Hello everyone. This is Jongmu Choi from Dankook University, South Korea. I'm a session chair of this session 3. Welcome and thank you for joining this session. In this session, we have 3 interesting talks. So let's start our session. The title of the first talk is polling-based Poker Workqueue management in XFS journaling. And the speaker is Do-hyun Kim from Korea Advanced Institute of Science and Technology. Do-hyun, yeah, let's start your talk. Welcome to the speaker.
Hello, I'm Do-hyun Kim from KAIST, and I will talk about our paper, polling-based Workqueue mechanism management in XFS journaling. So file system journaling is used for guaranteeing the integrity of file system on the storage device in case of unexpected system failure. The journaling of file system usually consists of 2 processes. We define these processes as in-memory logging and on-disk logging. In in-memory logging, the file system inserts the file system modification into a list. The file system modification, which is called the log, can be either a whole page or a copy of updated region of metadata object. Through the log list, in-memory logging delivers the log to the on-disk logging process. In on-disk logging, XFS synchronize the in-memory file system modification to the storage device. To do this, file system stores the log data in the log list to the storage device. Most popular Linux journaling file systems, XFS and ext4, use the journaling mechanism, which is optimized for the small number of cores and slow hard disk. It cannot effectively utilize the modern hardware environment, such as large number of cores and high-performance storage device that supports the high I/O parallelism. For instance, they have only a single global object, the log list, that multiple logging processes access. To avoid the last condition, log insertion and removal should be done exclusively. For exclusive access, they use the lock. In many core system environments, the lock contention on this list becomes substantial. And also, in on-disk logging, only a single thread dispatches all log at a time. This method cannot utilize the I/O parallelism of modern storage device. Due to these limitations, the scalability issue of file system journaling has been pointed out. Recently, many studies are being conducted with the aim of improving the scalability of file system journaling. Some studies propose the POCO management. They separate the journaling process and associated data structures on a POCO basis. The iJournaling and gjournal was implemented based on ext4. Former one applies the POCO operation log layer on the top of the ext4 journaling, and gjournal separates the journaling process on a POCO basis. Scale XFS resolves the scalability bottleneck of XFS by using the POCO data structures and lock-free mechanism. And Scale FS decouples the in-memory file system and on-disk file system, and it adopts the POCO operation log for POCO data structure to make the scale of file system. The other works use the lock-free data structures or propose new journaling schemes. SpanFS use multiple microfile systems, and BerryFS use the auto-preserving I/O stack to apply the new journaling schemes. These works are all based on ext4. Furthermore, there is a study for the scalability of a low structure file system next. In our work, we focus on the scalability issue of XFS journaling. XFS is the Linux journaling file system, which is introduced by SGI in 1993. It is the default file system for Red Hat Enterprise Linux, and it has emerged for the development of terabyte scale file system which is not supported by then file system. And it also supports multi-granularity differential logging, so it stores the only update region of metadata object, not the 4 kilobyte 4 page to the storage device in on-disk logging process. This slide shows the process of XFS journaling. Especially, it shows the process of on-disk logging, which we are going to mainly address. On-disk logging is triggered periodically or when fsync is invoked. Then it removes all the log in the global list and copies it to the log buffer. The log buffer is the data structure which temporarily maintains the log data that will be stored into the storage device. After copying the log, XFS dispatches the data of the log buffer. Lastly, once the completion interrupt of log buffer write occurs, XFS cleans up all the log data in the log buffer. On-disk logging is performed on two different threads. We call this thread journal thread and commit thread. The journal thread is responsible for the first part of on-disk logging. It copies multiple logs to the log buffer and dispatches it. The journal thread does not wait for completion of disk I/O. So most time-consuming process in journal thread is memory copy. After that, if the log buffer data has been synchronized to the device, XFS initiates the commit thread. The commit thread fills up the zeros to the buffer and notifies that on-disk logging is done to the other threads that waits for the end of on-disk logging. This slide shows what happens in the application thread that calls fsync system call in XFS. Overall, the process of fsync system call first initiates the on-disk logging and waits for the completion of on-disk logging. In XFS, the application thread that calls fsync waits for the completion of each thread sequentially. To do this, XFS uses the Workqueue. The Workqueue is the queue maintains the context of the thread waiting for a specific job to be done. The application thread pushes itself into the Workqueue and builds the CPU resource. After that, once another thread completes the process which the thread waits for, it wakes up the thread in the Workqueue. XFS uses the two different Workqueues for waiting two different threads. To simplify the explanation, we call these Workqueues journal thread Workqueue and commit thread Workqueue. Let's see the detail. Once fsync is invoked, the application thread initiates the on-disk logging. And then it waits for the completion of journal thread in the journal thread Workqueue. The journal thread copies the log to the log buffer and dispatches it to the storage device. And it wakes up all the thread in the journal thread Workqueue. So the application thread wakes up and goes into commit thread Workqueue. In this Workqueue, the thread waits for completion of disk I/O and process of commit thread. Once commit thread is done, it wakes up all the thread in the commit thread Workqueue. Finally, the fsync system call returns in the awaken application thread. Now is the Workqueue that supports async execution. The Workqueue is the queue maintains the functions to execute, and the Workqueue executes the queued function asynchronously. It contains one or more thread pools. The number of the thread pools depends on the configuration. Sometimes it creates only a single thread pool, and sometimes it creates a thread pool for each NVMA node. Each thread pool has its own queue, which is called full Workqueue. When the thread needs to execute the function asynchronously, it inserts the entry with the function pointer into the full Workqueue. One of the idle threads in the thread pool keeps checking the status of full Workqueue, and if it is not empty, the thread executes the function that contains in head of the queue. XFS uses the Workqueue for async execution of undisclosed logging threads. The function for journal thread is inserted into Workqueue periodically or when absync is invoked. The function for commit thread is inserted into Workqueue when the completion interrupt of log buffer write occurs. XFS uses the two different Workqueues for each type of thread. Now is the motivation. In this work, we first evaluate the two-part system, XFS and Scale XFS. Scale XFS is the most recent variant of XFS part system. We run the Xsim server workload on XFS and Scale XFS, and this workload is the absync intensive workload. The workload runs with the Intel Optane 905P as a storage device, and it runs on 112 cores machine. This graph shows the throughput of the Xsim workload with varying the number of cores. As you can see, the performance of the part system failed to scale and even collapsed after the 40 core. In XFS, the throughput of the maximum cores is only 74% of the maximum throughput. To identify the problem, we measure the log wait time in Scale XFS with Xsim server workload. The log wait time is the time for acquiring the log. Once the thread fails to acquire the log, the thread is blocked until another thread releases it. Since the thread cannot proceed with its activity, it harms the part system performance. The figure shows the top three XFS-related logs with respect to the log wait time. The x-axis shows the percentage of wait time for total log wait time. These logs wait time accounts for 41.5% of wait time of all logs. In this figure, each log protects the global wait queue and work queue used on this logging. Large amount of time is consumed for acquiring the log of the wait queue and work queue in XFS journaling. For more detail, the first two logs controls the access of the journal thread wait queue and commit thread wait queue respectively. Especially, the log that protects the journal thread wait queue incurs main log contention. The log wait time of this log is 23.7% of total log wait time. For the wait queue, all threads in the queue try to wake up at the same time when a certain condition becomes true. In XFS, all waiting threads try to acquire the log when they are waking up. So, if a multiple thread invokes the absync system call frequently and access the global wait queue in many core environments, the log contention on the wait queue becomes severe. The third log is for the wait queue, a work queue. It controls the insertion and removal of the entry in full work queue. If the multiple thread call absync system call, since all threads should acquire the log of the full work queue to initiate the journal thread, the log contention on full work queue becomes noticeable on absync intensive workload in XFS journaling. To resolve the log contention avoid from the global work queue and wait queue, we propose two techniques. First, we propose to use the per core full work queue to elevate the log contention on full work queue. Second, we propose the polling based on disk logging to avoid the log contention avoid from the wait queue. We apply the proposed techniques to Scale XFS, most recent variant of XFS. Currently, XFS uses the per NUMA node full work queue. The work queue creates the thread pools in a per NUMA node basis. The full work queue is also located for each NUMA node thread pool. To avoid the race condition, the threads that access the full work queue have to acquire the log for the full work queue. When the number of the cores on the NUMA node increases, multiple cores try to acquire the single lock, and the lock contention becomes severe. To address this problem, in Workqueue pull Workqueue, the Workqueue creates the thread pool and pull Workqueues in a Workqueue basis. The thread accesses only the pull Workqueue in the core where it operates. Two or more threads cannot try to insert the entry into the same pull Workqueue at the same time. So the lock contention on the Workqueue among the insertion of the entry disappears. In polling based on disk logging, we remove the wake mechanism for the journal thread and exchange it to the polling-based mechanism. In polling-based mechanism, the journal thread updates the indicator variable once it completes the process. And the thread that calls fsync system call keeps checking this indicator variable. It does not insert itself into the wake queue, and it does not build the CPU resource while waiting for end of the journal thread. Due to the elimination of the wake queue, the lock is no longer required. Through this technique, we can avoid the lock contention avoided from the wake queue. However, this method uses busy wait, so the thread occupies a CPU core and sometimes compete with another thread to get the CPU resource. On the other hand, the original wake mechanism yields all CPU resource by sleeping until the job is done. Due to this, we carefully adopt the polling-based mechanism to optimize the system. We only remove the journal thread wake queue and exchange it to the polling-based mechanism. We choose this one between two wake queue due to high potential and less overhead. Here are two main reasons for this decision. First, the journal thread wake queue shows a larger lock contention overhead than the commit thread wake queue. It means that the polling-based mechanism can lead to higher performance benefits for the journal thread wake queue. Second, for the journal thread wake queue, the time for waiting process is relatively small. This is because the application thread that calls fsync waits for the memory copy at the journal thread wake queue, while it waits for disk I/O at the commit thread wake queue. The related small time means that the polling-based mechanism would waste fewer CPU cycles for the journal thread wake queue. Now is the evaluation. To evaluate our work, we use the 112 core machine with 112 core machine with 512 GB RAM. The server has the 4 sockets and 28 core CPUs on each socket. And for storage device, we use the Intel Optane SSD 905P. And the CentOS 7.4 operates this server. We apply our techniques to scale XFS in Linux kernel version 5. We measure the lock wait time and evaluate the throughput of our techniques against XFS and scale XFS. We denote our work as scale XFS PB in the figures. Each graph shows the wait time of lock for pull Workqueue and journal thread wait queue respectively. We run the manual workload with the post thread directory. For this workload, each thread has its own working directory. So each thread does not compete with each other to access the same directory. The left one is for the pull Workqueue lock, and the right one is for journal thread wait queue lock. The y-axis is the lock wait time and lower is better. Compared with XFS, in scale XFS, the wait time of pull Workqueue lock and journal thread wait queue lock increased by 8.6 times and 5.3 times respectively. Scale XFS resolved the main lock contention among in-memory loggings and between in-memory logging and disk logging. It achieves the higher performance compared to the XFS file system but it does not address the other locks such as full lock and wait lock. In scale XFS, as more are performed during the same time, the overhead of these locks increases. Our technique effectively reduces these locks wait time for all file system, XFS and scale XFS. For the wait time of the lock of general thread Workqueue in figure B, lock overhead decreased by 73% and 97% compared with XFS and scale XFS respectively. This figure shows the throughput of the XIM server workload on XFS, scale XFS, and scale XFS PB with varying the number of cores. Y-axis is the throughput and higher is better. Our technique achieved the 28% higher performance than XFS and scale XFS in XIM workload at 112 core. This XIM server is AppSync-intensive workload. We reduce the latency of AppSync system call by eliminating the lock acquiring time. So our technique shows the higher performance for AppSync-intensive workload. And also, we elevate the performance collapse in XIM server workload. The performance degradation reduced from 26% to 10%. To conclude, we find the scalability issues of XFS and scale XFS, and we identify that there are severe lock intention on data structures for async and await mechanism used in on-disk logging. These mechanisms incur the lock contention overhead at the global Workqueue and global Workqueue. To address this problem, we proposed two techniques. First, Workqueue full Workqueue to elevate the lock contention on full Workqueue. And second, polling-based on-disk logging to remove the global Workqueue and associated lock. By using this technique, main log overhead from XFS channeling decreased by 97% compared with the scale XFS. And throughput of XIM server workload increased by 28%. Furthermore, in this workload, performance collapse is mitigated through our techniques. Thank you for listening, and please feel free to ask questions. Thank you.
Okay, thank you, Do-hyun. Nice talk. Are there any questions? Do-hyun,
Yeah.
please check the chatting window. There are one questions from online. Yeah.
First of all, thanks for nice question, great question, and I will answer the first question first. Audience asked me to if there are not many cores in the system, does the overhead too high? And actually, that's right. But in our work, we only consider the many core environment. For example, the scalability issue of the file system journaling occurs in the modern hardware system environment, such as large number of the core. So we only consider there are many cores in the system, so we does not consider there are not many cores in the server. And the next question is does NUMA multi-node system affect the locking performance of the proposed design? Actually, the for NUMA node Workqueue is this, but in our experiment, we does not see the negative impact of the Workqueue Workqueue management in XFS journal. It means that there are no high traffic of the data movement in on-disk logging of the XFS journaling. So XFS journaling does not need the NUMA-aware system and for the journal thread, and so we adopt the Workqueue Workqueue management.
Okay. Are there any other questions?
Is there one more question at the chatting room? So
Okay. Yep. Keep
I will
going.
answer the question. The audience asked me question, if there are multiple storage devices for the file system, does your design consider like multiple queue issue? Actually, we only focus on the locking mechanism of the exceptionally. So first, at the first of my presentation, I mentioned about the current journaling mechanism cannot utilize well the high parallelism of the modern storage device. But in this work, we only focus on the locking mechanism. So our design does not consider the multi-queue of the storage device.
Hello, can you hear me?
Yeah, I can hear you.
Okay, I have one question.
Yeah.
I think you have divided a log into multiple small logs per core, right?
In this works,
Yeah.
actually,
So actually
yeah,
the question is, how did you manage
yeah.
the number of cores per core logs from a large scale log, single data structure? You should
Uh,
have hundreds of cores and there should be multiple per core queues,
yeah.
right? And the log should be a single huge data structure, right?
Mhm.
So how did you divide the single huge log data structure into smaller per core data structures?
Okay. Actually, we only change the work queue as the POCO basis. Uh, I understand you means that the logarith becomes the POCO logarith, but in this work, we does not consider the POCO logarith. We only consider the POCO work queue management.
Okay, yeah, it means
Yeah,
you are assuming that there are enough number of um, works, right? Works on the work queue.
yeah, right.
Okay, thank you.
Yeah, thank you.
Okay. Any questions? Actually, I have one. Dohyun, I think you do evaluation with two operating systems, CentOS and Linux, right?
We only consider the CentOS, the
Se-
also
Okay.
stream. Yeah.
Okay, I see. Okay. Uh, any other questions? Okay, yeah. It's the end of the first presentation. Thank you to the speaker, and let's give a big hand to the speaker. Okay, okay, I will briefly introduce you, Professor Yu. The speaker is Sihan Yu from Dankook University, South Korea, and his talk is related to storage hierarchy in modern key value store. Okay, welcome to the speaker.
Okay, thanks for the introduction. Actually, you can, I think there are many Chinese people here, and you can remember me by my name, Xihuan. Xihuan means love, so you can easily remember my name. Today I'm going to talk about storage hierarchy in a modern key value store. We have experimented several tests on different sizes of database, and I want to analyze I want to share some of analysis to all the audiences. So key value store
Professor
is,
Yu,
okay,
please convert to the slide mode.
does it work?
Yeah. Yep.
Okay, so key value store is one of key application for big data systems. Many companies and many experimental systems and research works done in around the key value stores application. And RocksDB is one of popular application developed by the Facebook, and LabelDB by the Google, DynamoDB by the Amazon. And performance requirements, recent performance requirements for the modern key value store is very interesting. This year's Usenix conference, Amazon has presented some data statistics from their key value store application, and they presented peak key value store query request is around 89.2 million requests per second, and that needs very tight average latency within a single. I'm sorry, this is microseconds level latency is required to handle those high peak load with high availability configuration. So in this talk, we focused on the storage hierarchy, and according to the size of the database, and that the access latency different appears, and we want to understand the performance of key value store, considering different scales from the CPU cache and TLB boundary to the memory and to the storage I/O. I think most of the audiences here understand the cache and CPU cache structure. The numbers in the right-hand side is Intel's Haswell 3.4 gigahertz i7 CPU. It's 3.4 gigahertz, so one cycle means 0.3 nanoseconds, and up to the level 1 cache, level 2 cache, and level 3 caches, there are different access latencies that defined. And to the DRAM, it takes about 60 nanoseconds, and that's about 60 times higher latency. And the average memory access latency is affected by the cache access latency and hit rate or miss rate of the cache data structure. So it means the working set actually affects the miss rate and the DRAM access latency. So what we tried to focus on was the hit rate can be an important matter in average behavior of key value store, and cache access latency is very small, and the DRAM access latency is 200 times higher. So managing data structure on proper level of storage hierarchy is going to be important more and more. And another background information about our application, the modern key value store, is the structure of RocksDB, and it consists of different data structures. Firstly, we have to talk about the mem table, the data key value pairs in the memory, so in-memory data structure. And there is another data structure stored inside the storage SS table, sorted string table. So if we put some data on the database, firstly, it goes into in-memory data structure called mem table. And when it is full, it is flushed into the storage and in form of SS table. There is some optimization related to mem table, SS table, and once it is full, then it changes into immutable states mem table, and there is a separate thread flushing the mem table data to SS tables to the storage. And inside the SS table, the storage, there are background thread that keeps working so that it can reduce the working set, which is called as compaction operation. And compaction merges SS table and keeps the recency order as levels. There are multiple levels in SS table, and keeps the recency order means new data is in lower level SS table, and when it is older, then it is compacted, merged into a new data structure, and stored back into storage. Another important data structure is called block cache. A block cache is a in-memory data structure that caches the data in SS table. So we will talk about mem table structure and block cache and then SS table. So this is how we look up data from the RocksDB. So all data is, it manages data in recency order in the mem table, block cache, and SS table. So firstly, it searches the mem table, which is in-memory data structure. And the mem table size is 64 megabytes. Of course, there are some options to adjust the size. However, the default size is 64 megabytes. And it uses the data structure called skip list. And the skip list is presented in the right-hand side. So skip list has multiple levels. Instead of using binary tree, we use skip list for range queries. There you can simply think there is in-memory data structure, 64 megabytes in memory, and then if it fulls, then it goes into storage. And part of many storage SS table data is brought up into memory when it is frequently used, which is called as block cache. So instead of directly searching for the storage, it looks up for the block cache so that we can minimize the access latency to our key value. So firstly, look up your data from the mem table, and then look up your data from the block cache. And then if you cannot find it, then look for the SS tables according to the levels. And they are organized in recency order. New data is found whether in mem table or block cache. It is returned to the user firstly, and if you cannot find any data in the mem table or block cache, then you eventually go to the SS table and look up your data using some filters. RocksDB is a popular database, key value store database system, and there are a lot of related studies. And PebblesDB tried to fragment the entire data structure into smaller parts, which is called guards. And there are some write latency optimization, considering the flush operations slow down. And there are some operations on the in-memory data structures optimization according to the cache alignment and GPU usages, which is addressed in FAST study. And there are some different kind of studies around the keys and values pairing so that searches can be much faster only by looking at the keys. So key values separated in the WhiskKey study, and index can be separately learned, having a separate structure for machine learning techniques can be applied there for efficient data search. So learned index has been presented, and new hardware such as persistent memory or NVM devices can also improve the performance. So there are different kind of studies very popularly appeared around the RocksDB application. So this is our very first perspective. We measure the RocksDB get latency with different size databases. So get latency, we instead of write latency, we just focused on get latency, which is very different from writing value to the database. And because reading and querying data latency is more important in many real-world application scenario. So we focused on the get latency, and our hardware used was Intel i7 CPU with 16 gigabytes memory on SSD, and we used different configurations for the RocksDB. And we found that there are different scales exist in performances according to the sizes. The mem table, block caches, and SS table sizes also matters, and access latency to those different data structures scales from nanosecond scales to milliseconds. Different scales of operations appeared. And these are kind of formulation for the get path. You may imagine that when you access mem table and you can find it, then the access latency is there. And if you miss in the mem table, then you have to look up for the block cache. So miss rate multiplied by the block cache access latency. And even if you miss there, then you have to access the SS table. So the total get latency can be presented in this way. And block cache operation can be further divided into two different pieces. Lookup and fill, and SS table operation can be further divided into hit rate and key value data access and index accesses. So our first expectation for different scales of data structures and different levels of hierarchy. Search data from mem table usually happens on the memory, and if it fits into cache, then cache operation happens in nanosecond scale, so it could be very small. If it miss, then search from the block cache, usually in the in-memory data structure, so it covers up to several and tens of microsecond scale. If you miss in the block cache, then you have to go to SS table. In that case, we have to access files in the file system. So we have to access storage, or you can access the page cache managed by the operating system. So microseconds level or milliseconds level latency can be appeared here. So to have sub-milliseconds get latency or single digit microseconds get latency on the peak load, then we have to understand all these different characteristics and properties. So holistic analysis is required. So the get latency on random read and hit miss pattern on cache actually affects the get latency, and access pattern working set size matters. So in upcoming experiments, we have changed the sizes of the database, and we changed the work access pattern so that both work access pattern and the working set, how those kind of factors affect the performances. So on the database size, the working set size is one of the major factor. The small size database, like 100 megabytes database, access latency components are presented here, and 80% of access latency actually comes from mem table accesses. And when, according to the size of database, as the database size increases, the access latency of mem table decreases almost by half, and then further reduces. So if your database size is about 2 gigabytes, then memory access latency reduces almost by 1/3, and the data block access actually increases, and block cache search and filling becomes as twice as the mem table access latency. So according to the database size, latency contribution by different components differently presented. And there are diverse factors contributing to get latency. And one of side note that we have observed in the previous experiment was mem table access time is still kind of large. So here, black bar presents mem table access latency during the entire experiment, and SS table access latency is presented in gray bar. And even in the 2 gigabytes of data, database size, mem table access latency is still as larger than the SS table access latency. And you think SS table goes to the storage device, and mem table just accesses memory. So for every lookup, for every get operation, mem table access happens always. And if you hit in the cache means mem table or block cache, then actually device access is not so necessary. So even missing the block cache would not access physical device IO. And actually, another important factor we have found was in this experiment, all the data accessed here by the mem table and almost all the data in the SS table is cached in the page cache managed by the operating system. So the access latency here is not exactly as the physical device's access latency, but can be significantly smaller than expected because operating system manages the page cache, and page cache can hold a lot of data, actually stores the SS tables. So mem table access latency with a small database, possible parameters that affect latency, skip list search algorithm can affect, and working set size for CPU cache TLB friendly data structure can affect the actual get latency. So experimental setting for skip list search, we intentionally created a very small sized 250 entries skip list and measured the get latency for 250 random key values and account the skip list traversal loop iteration, and we check the correlation between the get latency with the actual algorithm's traversal times. And if the size is slightly larger than the cache size and TLB size, then it may lead to cache miss and TLB misses and how they affect. We present the get latencies, measured get latencies for 250 random read, and it presents the cache misses and TLB miss impact. So for the minimal size skip list database, for 200 entries skip list, the size is very small and it fits into L2 cache, and the lookup time get latency is very small, as sub microsecond level. So it goes to several nanoseconds, and the latency for the get operation is very strong correlation with the loop count. So algorithm overhead is very small. And if the size increases to the 28 megabytes, then our cache, our CPU has 8 megabyte CPU cache, and the size of 28 megabytes is larger than the cache, so you cannot put all your data in the cache, CPU cache, but it is smaller than single mem table size, so you do not have to access, hypothetically, you do not have to access to the IO devices or block cache. So this is the raw latency values, and we can see 3 different bands in the latency. Black lines here consist of 1 band, and that's usually most of the operation happens around or under 1 microseconds. And there are some bands, small spikes, and these are 99%, 97 percentile tail latencies covers up to 5 microseconds latency. And there are some higher spikes, rare spikes, and those are only about 0.03% tail latencies are there. And these are the latencies, and we further investigated where actually those kind of data value came from. And we further investigated the TLB and cache misses from the pub for profiling result. And we can see there are small TLB misses, and cache misses is slightly higher than expected. And LLC misses happens around these numbers. And we believe that TLB miss accounts very similar to the outliers in the upper bands. So we see that TLB has a huge impact on those high band, higher latency values in memory access. So these are the numbers presented in CPU manufacturer's information. So 64 bytes is cache line size, and 496 bytes are one page. So page boundary cross penalty means TLB miss penalty is about 6 times higher than cache miss penalty. So we found that TLB and cache miss affects the latency values, and that's around about in most cases for small working sets, 5 microseconds is usually the boundary. And if you missing the cache, missing the TLB, then your latency can go up to 10 microseconds. And we found that TLB, so uniform access and GPN accesses, and GPN, of course, presents better and tighter tail latencies. So summary for memtable access latency for a single memtable size database for very small skip list traversal latency less than 0.5 microseconds. If it fits in the cache, access latency is less than 5 microseconds. If you cannot fit in the cache, access latency spikes up to 20 microseconds. And skip list has some shortcomings. So label is randomly chosen when you put your data into skip list. And one more thing we importantly found was it is not frequency based. All those RocksDB data structure is recency based ordered. So even if you frequently access data, if the data is found in the SS table, then you have to go through all these mem table and block cache and then access the SS table. And skip list is based on a list data structure, which is not cache friendly. So those are kind of future works that to optimize the memory access latency. Block cache case, we found different access patterns, and the working set actually affects the performance of block cache. For the GPN access, get latency, the right-hand side graph is CDF function of get access latency, and IO access latency and get access latency, two different latencies actually came from block cache hit and miss. If you hit in the cache, then the access latency is slightly tighter. And if you miss in the cache, you have to go through the SS table and then bring your data to the block cache. And so the access latency has small gap here. And our observation shows block cache effects has 5 to 10 microseconds additional latency for the missed block cache accesses. So, and for the 120, the block cache size, default block cache size is quite small, 128 megabytes. And for 1 gigabytes and 5 gigabytes data, we measure the get latency. 1 gigabytes and 5 gigabytes have different number of SS tables, and 5 gigabytes have a much larger working set. So more SS table lookup is required. So the increased latency is presented. So accessing multiple SS tables around the multiple levels increases the access latency. So the latency differences actually came from the file system's I/O operations. And another important observation in our experiment was compaction. Compaction is SS tables access, and when the SS table size becomes too large, then it's merged, and it does merge sort and puts your merged data into next level SS table. So random read for 5 gigabytes of data. So normally 5 gigabytes of data, if you have 5 gigabytes of data, then compaction occurs. However, we intentionally configure two different options for one for doing compaction and the other for disable compaction, so that we can see the compaction operations impact. So when it is enabled, then compaction begins with the measurement. When it is disabled, then it is identical to previous experiment, 5 gigabytes data surge. So without compaction, I/O access happens around, usually you can get almost all the data within 20 microseconds. So block cache accesses. If you're missing the block cache, then you go to the file system, access SS table, and the latency for the 99% is around 100 microseconds. However, there are some spikes here, and the latency spikes is almost 100,000 and is very close to milliseconds level. I/O latency goes up to milliseconds level, and tail latency of 99% is about 1 milliseconds. But in many cases, we can get our data from the block cache, and that's around the 200 to 300 microseconds. Interestingly, compaction, when we enable the compaction, yeah.
Yeah, 1 minute, please.
Okay, I will finish quickly. So compaction shows very interesting result. At the very beginning, we can see very high peak in get access latency. It's about hundreds of milliseconds. So when you do compaction, the get latency can be very high because the compaction operation interferes with the get operation and accessing SS table. However, after the compaction completes, compaction completes around 5 millis sequences, and after that, the access latency is much smaller compared to previous case. So here the figure shows much reduced block cache accesses latency and I/O accesses latency. That's because compaction during the compaction, I/O operations are very intensive, and it can increase the get latency. However, after you compact, then effective working set becomes small, and you can save the space for more data for effective block caches, and you can reduce the working set size. So the last slide, in this paper, we look for some analysis around the caching strategies around the mem table, block cache, SS table sizes boundary, and mem table size data. Cache TLB utilization actually matters, and to keep the single-digit microsecond access latency, those data structure has to be very CPU friendly, TLB friendly, and it uses skip list and cache unfriendly behavior still observed. And for SS table, compaction leads to 100 millisecond latency. And after the compaction, I/O latency reduces by 1/10 due to reduced working set. For the block cache, it efficiently reduces the latency, hides latency for the I/O operation, and tens of microseconds latency appears and affected by different access patterns and the working size. So that's the summary of my presentation, and I will be very happy to have questions.
Okay, thank you, Xian. And please check the chatting window. There are several questions.
So, Professor Chang, so what's the point of the first question? This is kind of experimentation.
The first question is that if the CPU case size is changed and the SSD table and main table size is changed, what's the effect of your design?
So according to the mem table size and the SS table size, okay, so all those different factors affect the performances, and the mem table size is in-memory data. So to maintain the latency small as much as possible, then it's generally good to have all your data in memory. However, that could lead to large latency when you write. It can affect the write performances. So that can be kind of side effect. And the cache size, if you increase the cache size, of course, you can quickly get the value from the cache. However, if you write something, then it is going to be updated and has to go through several different levels of caches. So the latency, write latency could be affected. Okay, so I think the second question is quite long, so we have to separately talk about it, and I will send you some answers after the meeting.
Okay, thank you. Yeah. Maybe you can answer my question outline because it is run out of time. You can answer the next one's question. Thank you.
Okay, real world, we actually try to use random data as much as possible. So this paperwork doesn't cover any real world data. However, we are working with the real world data actually came from open data set. So for now, random data set, we generally random data, however, can be compromised. So different result can be appeared when you have a more efficient key and index search design.
Okay, thank you.
Okay, Professor Won, the overhead Bloom filter, actually, we didn't cover details about the Bloom filter's operation in here. SS table lookup actually is based upon Bloom filter operations, and Bloom filter covers up to, so to find your data is in the SS table or not, we are using Bloom filter. And as the data set increases, the Bloom filter can efficiently find your data in your SS table or not. However, reading the Bloom filter part, index part in the SS table actually takes time, and index accessing and is not the key value data. Index data access is actually the overhead of getting data. Of course, getting the key value pair from the data parts actually takes time, but majority of access latency comes from the Bloom filter access. I hope that answers your question.
Okay, Xian, there are another questions above the one's question. Yeah.
Professor Choi actually talked about that, just covered that.
Okay, thank you. Yeah. Due to the limited time, let's stop now and do discussion later after this session. Thank you, Sean, again. Yeah.